Okay, so we are looking at kinetics and equilibrium, note page 212. So we need to just quickly remember ideas about heat transfer during a phase change. So similar ideas to page 210. So a solid changing to a liquid. So going in this direction, we would say that the sample is melting, so it melts. And because it is melting, the solid needs to absorb that heat energy. And if it's absorbing it, that means we have a positive inflow of energy. Okay? Now, for the liquid to return back to the solid, so moving in the opposite direction, we would say our sample freezes. And in this process, the liquid must release energy in order to do that. So since heat energy is leaving the sample, it's getting rid of it, it would be a negative value. Now, a liquid changing to a gas, a liquid, in order for it to boil, it must absorb energy. So that would be energy going into the sample, so it's positive, but a gas returning back to the liquid state, we say, I'll write that down here, it condenses, so it must release the energy, and therefore we would have a negative sign. So positive Q or negative Q. So the amount of heat either being taken in or removed from the sample. So now we're going to talk a little bit more about compounds and their heats of formation. How this is the amount of energy transferred during the process of making 1 mole of a compound. And the energy transferred, depending on the compound, it could be absorbed or it could be released. Okay? So heats of formation are for making a compound, where elements are assigned a heat of formation value of 0 kilojoules per mole, because elements are our simplest unit of matter to exist. So for us here on Earth, elements are not created or destroyed. They already exist, they're there to use, so we're not forming them, so they are assigned a value of 0. So heat of formation, okay, I want you to think about your table I, and this would be a delta H value. So if it's a positive delta H value, that means that in order to form that compound, it's an endothermic process. And in the end, the reactants have less potential energy than the products. Therefore, the reactants had to absorb energy in order to make those products. So we might have our potential energy diagram, okay, that's the diagram with the 2 platforms in the hill, and reactants are always closer to the y-axis, so the y-axis represents PE, and so since the reactants didn't have enough energy, its platform is lower, the product's platform is higher, and we have a hill that connects them. So if we had scaling, you would see that the products, so I'm going to put a P here for products and an R here for reactants, the products would strike the y-axis at a higher value. Now, if you have a negative delta H value, that means that the process went through an exothermic reaction, and in this case the reactants had more potential energy than the products. So in order to make the products, the reactants had to release or get rid of energy. So our potential energy diagram has similarities, but will look a little bit different. So the y-axis is that potential energy. It will still have the two platforms and the hill, but this time the reactant platform needs to be higher than the product, and we still need that hill to connect them. So the starting platform, what starts the reaction? The reactants, and then the last platform, the lower one, P4 products. Now, to calculate the delta H, it's a delta value just like delta T. So whenever you calculate a delta value, it's always your final minus the initial. So a delta H value is based upon the difference between the heat content of the products, because products are how we end a reaction, minus the heat content of the reactants. So it's another delta H value, products minus initial, whatever is final minus the initial.